Sir?
So is it physically possible when the two particles go, you measure, let's say, the direction and spin of one of them, and then you change it, flip it from a minus one to a positive one, and then measure the other one? You do that?
Once you've made the first measurement, the entanglement is broken. Yeah, and that's a little, quantum entanglement really is fragile. After the first measurement, they're no longer entangled. And that's also why entanglement dissipates, because in order to measure my particle, I have to interact with it. And that allows me to make some predictions about the second one, but that interaction now creates a very different kind of a state in which that original entanglement is no longer there for me to use. I can only use it once to make one prediction, and then it's gone. Sir?
So when you had the two particles, you made your first measurement. How long does it ever dissipate, or do you wait a long time to make the second measurement?
As long as you good question. As long as you have kept these things, the other particle isolated from its environment, you found a way to kind of protect it from stray air molecules or whatever, then you can wait as long as you like.
In fact,
it doesn't decay with time.
There's some relatively recent experiments.
That's right. Yes.
Where they measured them strictly at molecularly very disparate times. Are you going to be talking about those?
I don't really have anything in detail to say, though I know that the physicist Gisin has done some quite interesting experiments where you've had entanglement preserved over very clearly macroscopic distances, like sort of a kilometer.
And also where the indefiniteness, if you will, of one particle seemed to persist in a way that would have required the other one to communicate with it back in time.
I
just love to hear that experiment presented.
Actually, this is something I've been meaning to turn my mind to, because I have read the reports about this in the popular press, and the semi-popular press. For example, sometimes in things like Science News and so on, what people say about these things does not bear scrutiny. And so, I have a suspicion that when one looks at that case carefully, there will be something weird and interesting there. I have no doubt about that, and I have no doubt that Gisin has done a really good experiment, but that the careful description of it isn't going to involve us having, backward causation. That's my strong hunch, because it virtually always turns out that way. Sir? Yeah.
I doubt we have any proponents of QM telepathy here, but I'm curious how solid is the theory and experimental state in terms of there's just no way telepathy could exist.
I want to separate the issues. Okay. Initial disclaimer. Do I believe in telepathy? No, I don't see that we have any particularly good evidence to think there is such a thing. Do I think telepathy is absolutely impossible? Hey, I don't get to make up the universe. The way the universe is isn't up to me. So for all I know, I don't think it's at all likely, maybe it is, but that's a separate question. That's the point I want to make. If, in my wildest imagination, it turns out that there really is such a thing as telepathy, the point is simply this, that quantum mechanics and quantum entanglement can't be the explanation, because the way that the quantum math works plugs that hole. There's no room in quantum mechanics for that kind of thing. Whether quantum mechanics turns out to be not the whole story and some other physical theory that allows this is true, like I said, I don't get to make up the universe, and if that happens, well, it happens, but it won't be a quantum story. That's my only point here. Quantum mechanics doesn't provide any basis for telepathy. Whether or not anything else does is a separate question.
Okay.
Yeah. Sir?
Can I follow up on my earlier question about it being a wave function? I just wondered about the possibility. So suppose you had the two particles speeding off the detectors, and suppose before they hit the detectors, you were to drop, let's say, a huge lead block down the path. If they were actually a physical wave function, wouldn't that stop any entanglement from occurring?
That's a good question. It would depend very sensitively on the physics, but the answer is not necessarily. Suppose that I've got, just think of it this way, suppose I've got my particle here and I've got my particle there, And we haven't gotten around to performing the experiment yet. But between the two laboratories, I erect a huge lead barrier, okay? Sort of running, as you might think, well, I'm just sticking this lead barrier between the two parts of this wave function. It wouldn't make a darn bit of difference. It wouldn't make any difference at all.
Have they done experiments like that where they just put a barrier before the detectors?
Well, let's put it this way. I don't know whether they have or not, but what I do know is this. If someone did an experiment and that made a difference, quantum mechanics would be wrong. Now, quantum mechanics might be wrong, but my point is that the theory itself says that what you have here, once you've prepared particles in a certain way, is a kind of correlation that isn't going to be affected by things like putting barriers between them or waiting a while. And so that's why, that's one of the many reasons why conventional attempts to explain this don't work very well. So just to repeat, if that made a difference, quantum theory is wrong.
But so far as you know, no such experiment has been done.
I'm willing to bet that there have been experiments that have been done that if you analyze them in the right way, would amount to something like that. I'm willing to bet that. Even though that might not have been the point of the experiment, that if you looked at what was going on, you'd see, well, yeah, there's all kinds of junk going on between these two things. It would have, in effect, had the same barrier effect, if a barrier effect were relevant. Barrier effects aren't relevant. That's the way they are.
They've done these action at a distance tests over like commercial phone line. I mean, special phone lines, but the answer is the phone lines aren't a straight line from place to place. They've had to turn around and go around corners because there are buildings in the way. They might have to go under a river. So, so in a sense, they put stuff in the middle.
Yep.
Yeah.
Yeah, in any routine experiment, there's going to be all kinds of stuff in the middle, but if it made a difference, it would have already made a difference. It's fascinating. I mean, it's a very different kind of connection than what we're used to thinking of classically, and that's why it's such a great subject to think about.
His idea of the phone line, that just means that the path is curved.
No, right. I understand, but all I'm saying is this, is that if quantum mechanics is right, barriers are irrelevant. It would only be relevant if the particle actually interacted with the barrier. And then you've got good old-fashioned ending of entanglement because you've got a new interaction. But if the barrier is just between the two, not interacting with either of them, quantum mechanics says it doesn't matter. Sir?
Yeah. Have you talked about the curious results of two polarizing filters and putting a third one in the middle? It's not entanglement, but
no, it's not entanglement. That is in effect that if you just had the three polarizers. I mean, I just have to say something quick because we don't have time to describe it for everybody. But that's a case where if it was entirely local, you could explain it classically by saying that each time you put the polarizer in there, it disturbs the particle in a certain way.
Can I say it? I mean, what we're talking. This is an experiment anyone here can
do
if you get 3 pairs of polarized glasses.
Yeah.
And this is the experiment, and if you can explain it, then you're ready for the next Nobel Prize. Here's the issue. Take 2 pairs of polarized glasses and turn them. The explanation you're being told is one is sort of let the light go only one direction, the other will let it go the other direction. Put them so they're 90 degrees apart so you see no light through them. Then you do something that if you can classically explain, more power to you. Take a third pair of polarized glasses. You would think if you put an additional pair of sunglasses in the middle, you'll have even less than 0 light coming out. I mean, it'll still be 0. Strangely enough, if you put the one in the middle so it's not at this angle or that one, put it at 45 or some other angle, you'll be able to see through all 3.
But classical electromagnetics
classically,
yes.
Classical electromagnetics explain that. No, classical electromagnetics would explain that. I mean, this would be an interesting conversation. But nonetheless, it is a good example because by working your way out from that example, you do find nice ways of explaining some quantum roots. So it is a good example. And when you talk about it with photons, you don't just have the good old-fashioned classical explanation. But classically, this phenomenon was understood. Anyway, folks, my voice is giving out, but you've asked lots of really good questions. I really enjoyed talking with you. And thanks for being a great audience.